Good morning, everybody. This is the continuation of yesterday's lecture, the lecture on 2-degree freedom vibration. So this is about free vibration analysis of undamped 2-degree freedom system. So in yesterday, the general form of 2-degree freedom system analysis have been discussed. And how to formulate the 2-degree of freedom vibration motion. And then we attempted to see some examples on 2-degree of freedom motion, means free vibration of 2-degree of freedom motion. So this is the continuation of yesterday lecture. So in our yesterday lecture, we have seen this thing. For free vibration analysis, there is no force. That means the name free vibration indicates there is no external excitation force. And the name undamped also refers to C1, C2, C3 is equals to 0. So we have left only the stiffness of material, the mass, and the coordinates. Okay, so this is free vibrational analysis of undamped 2-degree of freedom system model. Okay, so in this, the equation of motion, the general equation of motion given in 1 and 2 for general case is reduced to this form. Okay, so in this case, we section this part to two discrete part. For example, if we make a section at this point, okay. Sorry. So if we make section at this this and at this point, we have left two masses with it is better to show you with a kind of sketch. Okay. Pointer, pin, where is pen? So if we section this from here, and here, we have left one mass 1, okay, with a spring constant k. Okay, let arrow be in this direction. So kx is the force, kx1, k1 x1 in this direction, k2 times x1, no, x2 minus x1 is for the first mass. So consider this one as mass 1, m1. So again, for the second mass, okay, the motion of this considered to this direction, x1 and x dot 1 to this direction. Similar to this, we have mass 1 here, the free body diagram of mass 1. Okay, mass 1, mass 2, sorry, mass 2. And this direction, k3 times x2, because we have this x2 experiencing compression towards to k3. Here still we are considering the compression of k3 and tension of k1 and k2. So both masses are moving farthest to k3. And then in this direction, we have k2 times x2 minus x1, the relative deflection between the two. So we have two systems of mass, and then taking the summation of force along x for mass 1 for the first case. So summation of force in the x is equals to 0, gives us this equation. Again, for the second mass, similarly, summation of force in the x for M1, M2, mass 2 is equals to 0 gives us the second equation. So this is equation of motion for this system. So the solution, just considering harmonic solution, because this is free vibration. So in free vibration, the harmonic solution can satisfy the form of equation. So considering a simple harmonic motion for two mass, for mass 1, x1 of t is equal to x1 cos omega t plus pi, where this x1 is the maximum amplitude of the mass 1 and pi is considered the phase angle. Again, x2 for the mass 2, which is x2 cos omega t plus pi. So one can generally write it x of t, simply x of t in vector form is equals to xi. Okay, I refers, actually here we can write I, xi cos omega t plus pi, or we can represent it as, okay, pi. So this is the general form of equation. Okay. Now here, okay, substituting this equation into this equation of motion, we directly obtain this kind of equation. So here we see cos omega t for the non-trivial solution. This cos omega t is different from 0. So just equating the term inside of square bracket to 0, we can get this kind of equation. This equation. So this equation simplified in the matrix form, we can represent it as M matrix, that is diagonal matrix, and X matrix means X dot dot plus some K matrix, okay, and X matrix, then which is equal to 0 form in the matrix presentation. Okay, so from this we can get this form of matrix. Yeah, so this matrix in this the term inside of square bracket again taken for finding the equation of frequency equation or characteristic equation, or we call that equation for the finding eigenvalue equation. Okay, so this x1 and x2 consider eigenvectors, and the term here provides our eigenvalues. Okay, so what are the eigenvalues? So then the determinant of this matrix is equal to 0 gives us this type of equation, and this equation is called the frequency equation or characteristic equation, or it is called eigenvalue equation. Or it means we are going to determine the eigenvalues. So from that, we can find two roots. Here it is the power of 4. In terms of omega, it is the power of 4. So considering omega square, roots of omega square, the two roots of omega square are obtained from this equation. Just we can consider this term as a in our mathematics, ax square. We can call this part. This term as, we call it as bx, and this term as c. So this is ax square plus bx plus c is equals to 0 type of equation. For that, we have a quadratic solution, two roots of quadratic solution. Once the determinant exists, then there is roots. So these roots are this equation. Okay, so from here we can find omega 1 and omega 2 that are called the natural frequencies of the system in the first mode and second mode of vibration frequencies. Okay, so then Substituting the value of omega 1 and omega 2, we can find the amplitudes of various amplitude of the motion in the first frequency and the second frequency. So x1 of 1 and x2 of 1 is the natural frequency, the amplitude of motion in the first mode of vibration. And x1 of 2 and x2 of 2 implies the amplitudes of the second mode of vibration. So in order to get this equation, what we can do for omega 1, we substitute in this general equation. This is the general equation given above. So we have omega simply here also omega only. So instead of this omega, we substitute omega 1 for the first mode. So the value of omega 1 substituted here, and then what we can get, the equation is the amplitude equation from here. And then we will go to the amplitude ratio. Okay, in the first natural frequency, what is the amplitude ratio? Yeah, so the amplitude ratio in the first natural mode is like this. So for the given system of here, for the given system, this system, what we have is this equation. So minus m1 omega 1 square plus k1 plus k2 over k2. Or someone can use second equation, means we have two equations. So both of them give the same answer. So this is for the second equation. Again, similarly for the second mode of vibration, that means substituting omega 2 in the equation to obtain x1 of 2 and x2 of 2. Okay, so what will be that? We substitute here x2, omega 2, here also omega 2 in the main equation. And our x1 and x2 is changed to x1 of 2, x2 of 2. These are the representations to identify the second mode. And the amplitude ratio becomes x2 of 2 over x1 of 2, which gives this from the first equation and this from the second equation. So finally, we can obtain R1 and R2. Okay, so this is amplitude ratios. So notice that the two ratios R1 and R2 are identical in this case, actually. And actually, this case, they are identical here. Therefore, xi of 2, I indicates the modes that I can be 1 or 2. So the normal modes of vibration corresponding to the two natural frequencies, omega 1 and omega 2, are given in vector form. So x1, vector x in the first mode is equals to this thing for first mode representation. We can also substitute, rather than x2, we can put R1, X1. So here, X1, X1, we have left 1 R1. So this X of 1 can be represented as, okay, in 1 R1, then X1 of 1. So this is the eigenvector representation. These are called eigenvectors. Okay. So here also the same thing. The free vibration solution then will be we substitute x1 of 1, xr1, x1 of 1. Then for the first mode, the free vibration solution becomes x1 minus 1 cos omega 1 t plus pi 1 r1 x1 of 1 cos omega 1 t plus pi 1. Similarly, for the second mode, x vector x2 of t represents this equation. So these are the two free vibration solutions. And here in this solution, we have 4 constants. Constant 1, okay, constant 2, and there are 2 constants which come from, okay, here also another constant, means this is 1 constant, second constant, third, and fourth. So this all should be determined. We have to determine these 4 constants. So how we can, for that we need initial conditions. There must be some prescribed initial conditions that satisfy the equilibrium of the system. Okay, so finally we superimpose the first, the amplitude of x1 in the first mode and x1 in the second mode be superimposed. X2 in the first mode and x2 in the second mode should be superimposed. Then finally, we can get the equation of motion. So that superimposition is this one. So x1 of t is equals to x1 in the first mode plus x1 second mode, which implies x1 of t means the equation of motion, the first equation of motion solution should be x1 of 1 cos omega 1 of t plus pi 1 plus x1 of the second mode cos omega 2t plus pi 2. Similarly, for x2 of t, we have, instead of x2 of 1, we substitute r1 x1 of 1. Just substituting this constant. So we have these 2 equations, equation number 1 and equation number 1 and the 2. So the unknowns are these 4 unknowns, which should be determined from considering some initial conditions. Just x1 node, we can call it as, here also x2 node, again here, this should be x1 node of dot, x2 dot of not of dot. So these things must be satisfied. So substituting these equations here, this is actually x1t, x1t. So instead of ton, we substitute x1 of 0, which gives us this equation 1. Again, the second x2 of t, which is x2 of 0, gives us, when we substitute instead of t0 in this equation, it gives us this equation. Similarly, for the first derivative of x1 and x2, the equation x1 of t and x2 of t, we will get this kind of equations. These are the derivative of x1 of t and x2 of t. So from this 4 equations, just looking into the 4 equations here, we can get the following expression. So in 4 equations, we can see x1 of 1 cos pi 1, x1 of 2 cos pi 2, x1 of 1 sin pi 1, x1 of 2 sin pi 1. Okay, the sine 2, this is 2. Okay, this is 2. So those things gives us this kind of equation. From where we can obtain these 4 equations, this one, we have this one. Again, here we have another equation. Here we have another equation. Here are some sign equations. So this is the combination of those equations. So yeah, how we can get, if we simply take this one, x1 0 is equals to x1 of 1 cos pi 1 plus x1 of 2 cos pi 2. This again, this. So just rearranging the equations, finally we get these equations. These 4 equations. Equation 1, 2, 3, 4. So this 4 equation helps us to determine the 4 constants. So the next step is just finding x1 of 1, because x1 of 1, this is square plus this square gives us x1. Why? Because this radical of x1 cos pi 1 square plus again x1 of x1 of still 1 sine square sine pi the whole square, which gives us obviously x1. Why? Because this gives us, we can take x1 of 1 square the whole times sine of pi 1 square plus cos of pi 1 square. So sine pi 1 square plus cos pi 1 square gives us 1. So from here we can get radical of x1 of 1 square. So it gives us x1 of 1. So x1 of 1 is equals to this square under radical plus this square under radical. So that means we have this square in the radical plus this square in the radical. Similarly, for x1 of 2, we make x1 of 2, this square plus this square gives us x1 of 2, which is equals to this square plus this square in the radical. Okay, so that is the expression here. Yeah, this is the expression. From that, we can obtain this general equation for x1 of 1. So this is one of our constant, which is easily determined from the initial condition. In the second case also, as we have this case there, for x1 of 2, the same procedure, we can get, this is x1 of 2. Another constants, we have constant pi 1 and pi 2. Okay. So pi 1 is equals to tan inverse of x1 of 1 sine pi over x1 of 1 cos pi 1. So that directly we substitute this equation there from the previous slide. So we can get this equation for pi 1. Similarly for pi 2 also, we substitute for the second phase. So this is the third and this is the fourth equation. So based on this discussion, we'll take a simple 2-degree of freedom motion. We have discussed it yesterday, but just for more clarification, we can take this example. So how we can find the natural frequencies and mood shapes? Our requirement here is finding the natural frequencies and mood shapes. Why we are finding the natural frequency? Once we know the natural frequency of the system, we can design our system not to make any resonance that directly coincide with the natural frequency of the system. So that is the aim. So here the equation of motion for this is m1 x1 of t plus k1 plus k2 x1 minus K2X2, which is equal to 0. And for the second mass, we can also take the same principle. We can cut it from here. We can take the free body diagram for mass 1 and the mass 2 separately. From that, for mass 1, we have this equation. For mass 2, we have this equation. And this equation in numeric value, because K2, K1, K3 are all the same, means if K1 is equals to K2 is equals to K3 is equals to simply K, that means we can K1 plus K2 means 2K. K2 simply means K. Okay, here K2 plus K3, 2K. Here minus K means simply K. We substitute these values and then we assumed harmonic solution of this type. Okay, and we substitute the value of, we differentiate this for 2 times and then substitute in the X place. So finally, from that, we can find this equation. So the determinant of this equation is equals to 0, means we can find the characteristic of frequency equation. Okay. So our frequency equation is this one. Okay. This is the frequency equation of a recent model. And then the quadratic roots of this frequency equation are this equation. So finally, solving this quadratic equation, we can get omega 1 square is equals to K over M, and omega 2 square is equal to 3 K over M. That implies omega 1 is equal to radical of K over M. This is the least, the smallest natural frequency that the system can vibrate. And the second smallest natural frequency is 3K over M and the radical. So these are the solutions. So now representing amplitude ratio. So what we can get 1 for the first natural frequency. So this one implies both masses are oscillating in phase with equal amplitude. That means x1 of 1 is equal to x2 of 2. So that means our system of mass are in phase. Okay, as the first mass move up, the second mass also in the same amplitude moved up. For example, if I consider this as an equilibrium position, okay, and these are mass 1 and the mass 2. So as this moved some x1 of 1 amplitude, then this also in the same position, x1 of x2 of 1, which is equal to x1 of 1. It shows like that. In the second case, and the second natural frequency, x2 of 2 over x1 of 2 gives us minus 1. R2 is equals to minus 1. So this implies x1 of 2 is equals to minus of x2 of 2. They are the same magnitude, but opposite in size. That means when one of the mass, let's draw the same thing. For example, if I consider this as a equilibrium position, okay. For example, one of the mass is at the above of the equilibrium position. Another mass is with some amplitude x. Another mass also in the opposite direction with the same amplitude. The same amplitude x. So they are moving out of phase. Okay, this is, for example, mass 1. This is mass 2. So they are moving one up and another in another direction. So their motion is out of phase. So this is the meaning of this -1 and 1. Okay, so for the natural modes of vibrations, in the first natural mode, our equation of motion that x of 1 of t is equal to x1 of t, which is equal to x1 1 cos of omega 1 t. So this is the representation of omega 1 t plus pi 1. And for this also same. So in the second mode also we have these two equations. So we will superimpose this equation plus this equation for the x1. x1 is equals to x1 of 1 plus x1 of 2. We superimpose this with this in order to get the first equation, and we will superimpose this one plus this one to get x2. So this is the representation. The general solution will be that steady state solution. This is not full solution, but the steady state solution in the general form, which is x1 of 1 of t plus x1 of 2. So we can get this equation for general form, or this one. Here also for the second equation is x2 of 1, x2 of 2. So we have this representation. This R2 is -1 here. Here R1 is +1. There is R1 here, sorry. X1 of 2 means yeah, that is R1 is here, R1. But it is 1, so that we simply took it. So what does this equation implies? Yeah, masses are moving, for example, mass 1 and the mass 2 in the first mode. One move up, the second one also move up. The second one down, the first one also moving down. Means they are in the same position, means they are moving the same. Okay, so that is the meaning. Sometimes they may move out of some phase. Means, for example, if this is reference position, if this is mass 1, okay, or second mass may be located here, like this. Means in this case, there may be some out of phase angle pi. Okay. Another second case, the two masses are out of phase, 180-degree out of phase. That means one is moving up, another one is moving down, and vice versa. So this is the mode shape for the second mode. Okay, so this is what we have learned yesterday. And then we are required to find x1 of 1, x1 of 2, two constants for amplitude constants, and the phase constants pi 1 and the pi 2. In the recent case, no problem, but whenever there is some system which is out of phase by some angle, then we need to find pi 1 and the pi 2 again. Okay, these are the four constants to be determined. How we can determine those four constants? This can be easily determined using the initial conditions, the prescribed initial conditions. Okay, here we have only the amplitude initial conditions, means the velocity and the amplitude of the motion will give us kind of some clue of the initial conditions. So applying the initial conditions and the equations, we have x1 of 0 is equal to x1 of cos pi 1 plus x1 of 2 cos pi 2. The first derivative of this one, x1 dot of 0 is equals to omega 1 x1 1 sine pi, omega 2 x1 of 2 sine pi. Similarly for the second. So we have this, and when we properly apply these rules, means substituting the values, what we can get, x1 of 1 cos pi 1, x1 of 1 cos pi 1 is this, have this equation. Okay, this equation. Again, x1 of 2 cos pi 2, cos pi 2 equals to this equation. Because we developed this at the very beginning, we can refer it back. Okay, that general equation is there. So directly taking those equations, we have this. Again, x1 of 1 sine pi 1 means sine pi 1 means this thing, x1 of 1 sine. So from that, which is equals to this equation, x1 of 2 sine pi 2, having this equation. So we directly substitute. Our R1 and R2 are known. R2 is minus 1, R1 is plus 1, so it gives minus 2. Here also the same thing. Okay, so this initial conditions of the velocity and the displacement are not given in numeric. Someone can take their value, maybe in terms of numeric value, then finally we can find. And here, from this equation, omega 1 is radical of k over m, omega 2 is 3 k over m. Substituting this thing, we can get this equation. Finally, taking these equations for x1, so 1 over 2 means minus 2 means this is minus, so minus 2. So just substituting the values. Yeah, so this is x1. In the same way, x1 of 2, x1 of 1 is this, x1 of 2 is following the same procedure. We can find this equation. And pi 1 is tan inverse of this quantity. So finally, this is the pi 1 and this is pi 2. So whenever some numeric value given, we simply substitute those number and we can calculate, or we can find these 4 constants. The second important part of vibration analysis is considering the torsional system. Okay, still what we have learned is the linear system. Okay, the vibration of linear system. Now let's see the torsional system of 2 degree of freedom. In this case, what we are talking is the shafts are most of the time rotating parts and which are subjected to torques. And then it experiences the torsional moment. So, and the material subjected to torsional stiffness. Okay, the stiffness we consider here is torsional stiffness. Rather than linear deflection aids, we use torsional twisting angle or theta. Okay, so if any number of shafts are connected, any number of discs are connected to the shaft, that indicates any number of degree of freedom system under torsional motion. Okay, so here we are talking about 2 degree of freedom. So we have 2 discs connected in a shaft, and sometimes the shafts may have variable diameter or different cross section. Okay, so we now consider a uniform shaft with uniform diameter, which is carrying two discs, okay, which are flywheel. Okay? So these flywheels are rotating with some RPM, and then there is a relative deflection take place in between them. So these all are under the consideration of here. So this is what we are going to talk. So in recent case, consider a discus, two discs, which is subjected to or connected to the straight shaft. Okay, this is the shaft axis. So the rotation of discus about this axis we consider, and when torque is applied, it is forced vibration. If torque is 0, then it is free vibration. Okay, so now let's, in general case, consider the torque is there. So the question of motion is just taking this free body diagram. Let's see, this is the free body diagram for each discus. This is disc number 1 and disc number 2. So the torque applied to disc number be T1, or we can sometimes use MT, means moment torque, MT, okay, MT1, MT2. And the stiffness to this side, KT1, stiffness at the middle, KT2, stiffness to this direction, KT3. So consider, and the mass moment of inertia of the flywheel of the disc, J1 and J2. Or this J thing, this R, I think 1/2 MR. Mass times R, the mass is given. Anyways, the mass moment of inertia of the discs are also there. Okay, there is here the twisting at this side, KT1, θ1, and the relative twisting here is KT2 times θ2 minus θ1, and the third portion of the segment of the section is KT3, θ3. So let's consider the first flywheel, or the first disc, and then develop equation summation of torque applied to first disc is equal to 0, gives us this equation. Means J1 θ1 dot dot plus CT1 plus CT2 θ1 dot minus CT2 θ2. It is almost similar to the previous general equation of motion developed. So which is equal to T1 of T. T is the torque. For the second disc, we have also this equation, J22 θ2 dot dot plus CT2 plus CT3 θ2 dot minus CT2 CT2 θ1 dot plus KT2 plus KT3 θ2 minus KT2 θ1, which is equals to torque 2, that's subject to time. Now let's consider undamped torsional vibration. Undamped torsional vibration means all the this CT part when, or the torsional the damping part will be 0. And if we consider free, again free, then the torques will be 0. Free undamped torsional system, then the torque will be 0. But let's see simply undamped, because here there is no damping representation. Sometimes our flywheels are rotating in some viscous damping condition, because some fluid media, if it is working in the fluid media, there may be viscous damping case in actual case. So that's why. So the next procedure which we have seen for the linear system is completely the same. It is a simple substitution of some parameters into this system. So to illustrate our discussion, let's take a simple example of torsional system. Look, a shaft which is fixed here and which is having two flywheel here, okay, and we have shaft this side KT1, the stiffness, and the middle stiffness KT2, and the shaft is having θ1, the relative deflection, means the relative twist, and the θ2 of the second shaft. So our free body diagram simply seems like this. This is a free body diagram of the above system. So what will be the equation? So in general, find the natural frequencies and mood shapes. Mood shapes means vibration modes, like whether they are in phase, out of phase, or having some angle. So for that, the mass moment of the disks are given. For disk 1, J1 is equals to J. For disk 2, J2 is equals to 2 J1, means it is 2 times J simply. So for that, we took the general equation like this. So just substituting the given condition. And KT1, KT2 and are the same. Simply this is KT. This is also KT. So we have no KT3 here. So by substituting on the general equation, we get J θ1 dot plus 2 times KT θ1 minus KT θ2, which is equal to 0. And the second equation is 2 times J, because J2 is equal to 2J. θ2 dot plus KT θ2 minus KT θ1 is equal to 0. So this is the equation of motion for this system. Now, assuming harmonic solution also, and substituting this harmonic solution into the main equation, we get this equation. And from that, we can find the characteristic equation by providing determinant of this part is equals to 0. Determinant of this is equals to 0 means gives us the characteristic equation. Okay. So the characteristic equation, this is the characteristic or frequency equation. And observing here, we have 2J square as A. We have minus of 5JT is equals to B. Okay. And the KT square as C. So just substituting this in our quadratic formula, finally we get omega 1 square is equals to 5 KT over 4J minus KT over 4J and the radical of 1 minus 7. And omega 2 is equal to 5 KT over 4J plus KT 4J radical of 17. So these are the two frequencies of vibration. Okay, so once we get these two frequencies, we determine the amplitude ratios in first mode and second mode. So in the first frequency, in the second frequency, this is okay, omega 2 square. So just substitute in this, what you can get, θ2 of 1 is equals to R1 is equals to minus of 5 minus radical 17 plus 2 over 4. So that gives us this relation, the relation between θ2 and the θ1 in the first mode. Here also, substituting omega 2 of 2 into this equation, finally we get R is equal to minus of 5 plus radical 17 plus 2 over 4. So this gives us this equation. So this is the general form of natural modes of vibration. So theta 1 of 1, so for theta 1 of 1, t is equals to this equation. Theta 2 of 1 gives this equation. So substituting our frequency values, we have this equation. Finally, for the second mode also the same representation like this. Then we'll superimpose the first one with the first one of the second, and the second one and the second one of the second. So we superimpose it, and finally we get the solution. General solution obtained by superposition. Okay, so after superimposing, we have this equation and this equation. These are the two solutions of vibration. And then in this, we have to determine again the four constants. We have one constant here, second constant here, third constant here, fourth constant here. And in two equations, the same, these problems are there. Okay. So we have to determine those things. Okay. So for that, we have to implement initial conditions in similar manner. So what are those initial conditions leads us to? So these are the methods we can determine initial conditions. It takes some patience to look it, please. So you can go through and you can see it by yourself. Here, these things are there. Okay. Yeah. Because it is vibration course, it needs a lot of patience to follow each of these things. So implementing this initial conditions, finally we can get theta 1 of 1, theta 1 of 2, pi 1, pi 2, like this. These are the solution of this equation. So thank you very much for your patience. This is all about today's lecture. So this is the end of